From here on out, we're going to concentrate on NVIDIA. First and foremost, this is by far and wide the most utilized system within scientific, or utilized vendor within scientific computing. Not to say that there aren't implementations using Radian graphics, but it's much less common. The idea being that most of your code is actually, that has been written thus far, is actually using CUDA and not OpenCL. And if you get an NVIDIA GPU, you can support both OpenCL code and NVIDIA code. So that's ideal. Within that, we have these GPUs. Again, my idea is not to cover the details of how to program in GPUs, but provide this service, GPUs as a service, if you will, within a normal cloud infrastructure. So again, like I said before, they're becoming commonplace within scientific computing. You can look at the current top 500, and a number of these new systems coming online have specific accelerator cards with as GPUs. It's because they provide a great performance per watt. You can get orders in magnitude scalability with a linear scale in watt usage. For instance, many applications are scaling 40, 50, 60, almost 100 times what you could do on a normal CPU, even a multi-core, latest generation, Sandy Bridge CPU, with only adding a couple hundred extra watts to your node. So there's massive amount of advantages there, especially as we move towards exascale, where the first class problem is power utilization. There's different methods on how to actually provide GPUs within a virtualized environment. The first and most research thus far is actually providing a remote API for CUDA, and I'll explain that next. But there's also the idea that you can use a GPU directly within a virtual machine, and is in many ways the most ideal. The idea with direct GPU usage is that it seems as if you use your GPU as you would on a normal host environment, except you're doing so within a guest virtual machine. And then there's, of course, like any technology, any set of technologies, advantages and disadvantages to both. So I'll talk first about front-end GPU API. The idea is that you have a API that looks similar to the CUDA API that currently exists, that will actually take those procedure calls and translate them over a network or through a shared memory system to a host, either on a remote machine or on a back-end host where you have a front-end VM. And it will actually execute that API call on a remote source. The idea here is users can share GPUs across a cluster where not every cluster has a GPU in it. You have a set of resources that have GPUs that run the daemon, if you will, and then on the front end you have normal CPUs which do your CPU code, and then when it's time to execute the GPU portions of that, they'd make the remote method invocation to these daemons, which actually execute on remote services and return that back. The next slide will clear that up in case that's a little bit confusing, but there's many implementations. I'm going to talk mostly about RCUDA, which is the most prominent, but there's also gVertis, which we have a deployed solution here at ISI, as well as vCUDA, gVim, and there's a number of others. This idea is not novel even when applying to other virtualization technologies. If you guys are familiar with doing 3D acceleration on VMware or Parallels on your given laptop, a lot of the solutions actually take this same approach, where they emulate the API of DirectX or OpenGL, for instance, and then translate those calls to the host CPU and talk directly to the GPU. There's obvious inefficiencies with that, but for right here, we can look at the process for doing a remote RCUDA invocation. So you have your application. Let's see if I can find my pointer here. Okay. We have an application, and that will make an API call to CUDA, or what it thinks to be CUDA, but is really the RCUDA library, which will then translate that call across the network to some server-side RCUDA daemon, which will then actually make the real call to the CUDA driver and runtime environment, which will then execute on your NVIDIA Tesla card or whatever other card you have that supports this, with the results returned, again, through the server side, across the network, and back to the application. The idea being the application doesn't actually realize that all that data is passed back and forth through the network. This works pretty well, actually, and the CUDA people have gotten pretty good results with it thus far for a certain type of applications, certain set of applications. But as with any technology, there's a number of limitations here. First and foremost, all your data is going across the network in some way, shape, or form, because anything that you do within the GPU, any data that you modify or you have to bring in has to not only go. Normally, there's a huge latency going across the PCI bus, but now you're actually going not only across the PCI bus, but out to a networking card across the network, and then to an entire remote site. Now, a lot of this depends on your interconnect that you're using. For instance, gigabit Ethernet is going to be a lot slower than RDMA and InfiniBand, but there are still notable limitations to this. And you can be affected by other communication mechanisms that are going on throughout your given cluster or cloud, if you will. Furthermore, a lot of these implementations either aren't full implementations of CUDA or are playing catch-up to the latest generation of CUDA. For instance, our CUDA just now caught up to CUDA 4.0 in terms of the API for all sets except for the OpenGL set, but there's still compatibility issues that arise for certain applications. So this isn't an ideal world that we're working in. Furthermore, you have to take your code and decouple the CPU code from the GPU code explicitly. They provide some like decompiler tools to make this happen, but the point to note is that you can't just take your application and go, oh, okay, I'm on the cloud, and drop it into place. You actually have to do a large number of modifications to this code and test from the get-go all over again, which is problematic. So what we really want to do is just have a virtual machine that looks as if it is running on quote-unquote bare metal hardware, and recently we're actually able to do this. The idea is to use a mechanism called PCI Passthrough. This is available originally through letting VMs utilize networking cards that are specifically not available from an emulated driver set and give it access directly to a VM. Now, previously, that sharing those networking cards becomes a problem from not only a multi-VM and host standpoint, but also just in terms of a security standpoint, where I may give sticking with a NIC instance, I may give one VM access to this networking card, this NIC. However, it may still be possible for another VM to listen through all that traffic. So there's no security or isolation available up until the use of VTD, which is Intel's version, or IOMMU, where it actually provides, from an architectural standpoint, a security mechanism and separation point for separating multiple PCI devices from virtual machines to truly provide isolation of a given PCI device directly to a VM. The idea here is we're not using any sort of emulated drivers and no special tricks here, where typically with emulated drivers you have to first have a guest VM talk to the DOM0 or the host controller, which then communicates to the hardware through a virtual machine monitor. Here we're bypassing that entirely. There is a current implementation that uses multi-GPUs provided by Citrix, and that's currently what's deployed on a small, what's called GPU cloud, or the GPU compute instances on Amazon EC2. But this implementation is a little bit different, but in some ways competitive. So to give you a pretty example here, first ignore the InfiniBand here, that's not really relevant for this. But the idea here is we have GPU drivers that bypass the domain 0 completely, as well as the virtual machine monitor, and talk directly through to a GPU it is assigned to over PCI Express using the VTD or IOMMU technologies. This removes a lot of latency that you would receive otherwise, and it enables very fast computation. Now you can also do this, there's recent technology that's come out to do this also with InfiniBand, but that's a separate issue at this point. So